All right, guys, a moment of silence for those that failed to return from the break. And now let's remember what we had been doing before the spring break. So first of all, you had an exam, correct, guys? And how are you faring with that exam? I mean, it's so amazing. The questions were so light, right? Am I right? Is that what happened? Or do you find the questions terribly difficult and scary? And of course, guys, show me your faces. I haven't seen you in so long. Good. We are talking about the same exam. I mean, I'm hoping you are not talking about the same exam, right? I am. Right? I would not find when I begin investigation that you have been working collaboratively with some other outside help, correct? That's not going to happen. You made sure to hide your tracks. Good. So, Fnul, remind me, what question did you find ambiguous on the exam?
Question number 3 and 8.
What were those questions? I don't have it on this computer, so I mean, I can find it, but I don't want to do it. So those questions were what specifically? So question number 3 asked to do what?
Like a traveling circus is moving in a train consisting of 20 cars, which
Okay,
were rent.
okay.
Yeah.
And what was confusing about it?
Like I was not sure how to solve this. Like, do I have to use any axiom of probability or like what?
Well, just do you see what is happening? So you imagine that you're a little child waiting for the circus to arrive, and you see the train coming, and then you first see the engine, yes, and after the engine, you begin to see carts, and you know the itinerary. You know that there are, I think, 4 carts containing lions, 4 carts containing animals, elephants, maybe, I don't remember, right? So there are 4 cards of certain types of creatures and some other cards. And those cards were attached to the train randomly. Good? And the question is, what's the likelihood? Imagine here it's coming, the train. What's the likelihood that I will first see one type of card and then the cards of the different types listed? So I don't remember which was the type I mentioned. Let's say, what's the probability? I think you will not be seeing lions before, well, after. You will not see elephants or other creatures before you see the first lion, something like that, correct? Good, so that was the question. Good. And then what was clear now what I mean, right? So it's like a sequence of cards. There are cards labeled lions, there are cards labeled bears, there are cards labeled clowns. And what's the probability that I will not see, I think, bears or elephants before I see my first lions?
Yeah. So like, do we have to ignore the other animals?
It's up to you. I mean, you can ignore them or not. It's for you to decide.
Sure. Thank you.
Yes. And then what other question? You said question number 8, and that was what?
Yes, it was regarding the monotone non-decreasing sequence.
Yes, monotone non-decreasing sequence. What about it? You wonder how to do that?
Yeah.
Yeah. So first try to think how do you record or recognize a monotone non-decreasing sequence. Once the exam is submitted, I will show you how to do that. At least I'll show you 2 ways that I thought of to do that. Okay.
What I'm thinking to solve it, like the way we did, the way we solved the toilet paper and hypochondriac.
Okay, maybe that's great. Maybe you have a great way to do that. Why not? Sounds like you might be onto something.
Sure. Thank you.
Good. Just think about it, write it carefully, and hopefully that works well. Good, guys? All right, so let's get back to today's lecture. Here it is. And think about it carefully. I'm not sure if you remember this question, guys. 3 prisoners. 1 was randomly picked to be executed. Now, prisoner number 1 is rather smart, and he wants to know from the jailer which one of the 2 remaining prisoners will be let go. Regardless of who is executed, one will be let go. The jailer tells him, well, I cannot tell you that information because I will affect your probability of being executed. So what do you think of that problem? Who is this information going to affect the probability of being executed or not? And then, of course, that involves thinking carefully, what is it that we're talking about when we speak of probabilities? So now you think it is 1/2? No, but so 1/2 after this information, how do you reach that conclusion that it's 1/2? Do you mean that there are, you see, you have to be careful. Just because there are 2 possibilities, that does not make it 1/2. You agree? 2 possibilities does not make 1/2. Maybe one possibility is likely and the other possibility is not. So let me help you guys, since we need to move on. Let me tell you how I thought of it. Okay. So first of all, how do I understand the question? I think given the information, right? So you see, when information is given, you know in what universe you reside. For example, if the jailer tells him you are going to be executed, the probability is 1. Why? Because the prisoner is now in a universe where he is executed, correct? So the probability can be affected by this information, because you understand what is the information doing. What you're doing in probability is you are looking at the total possible universes in which you might reside. And your lack of certainty is correlated to your lack of knowledge about the particular universe in which you reside. Because once you know the universe, everything is certain. You understand? Once you know all the entries in that huge Kafka protocol, everything becomes completely certain. That's the position from which I look at it. Good. So the information makes the number of universes narrow. Now it might affect the probability or it might not, because even if I reduce the number of universes, I might similarly by proportion reduce the number of universes where the outcome is my execution. You see? So for example, if I reduce the total number of universes by a factor of 7, perhaps I also reduce by a factor of 7 the total number of universes in which I am to be executed if I'm prisoner 1. And that does not affect probability. Let me just release my beast. Now I'll be back with you. Good. So let's try to see what can happen, guys, by analyzing Bayesian, by doing Bayesian analysis. So let's E sub I be the event that prisoner number I is executed. Initially, the probabilities are 1/3 because it was random selection. You agree? And what does the 1/3 mean? It means that if you take all the universes and exactly 1 out of every 3 universes, prisoner 1 is executed. In 1 out of 3 universes, prisoner 2 is executed, right? Good. So the probability is 1/3. Now let n denote the event that jailer will name prisoner number 2 as the one to be let go. Okay, so you will say prisoner 2 is the one to be let go. So I want to know what is the probability of prisoner 1 executed given this information that prisoner 2 is the one released. You agree that whenever this information comes around, without loss of generality, you might for a moment think, well, maybe it's prisoner 2 mentioned. Perhaps without loss of generality, perhaps it is loss of generality. But let's see how naming prisoner 2 might affect the probabilities. So probability E1 given n I just recondition. It's probability of n given E1 times probability of E1. That means if the jailer knows that prisoner 1 is going to be executed, what's the probability that person number 2 is named as the one that will be released? You understand? So then on the denominator, I just write what's probability that person number 2 is named. It's number 2 named given person 1 is executed, number 2 named given that number 2 is executed, number 2 named given that person 3 is executed. Clearly, the middle section is 0. Do you agree? The person cannot be, if it's person number 2 who is executed, it cannot be the one to be let go. Yes? So we have 0. Now here is the assumption I will make. Okay, I will not know. Basically, if person number 3 is executed, then the jailer has no choice but to name person number 2. Right? There is no access to person number 1. There is information is not going to be released. Only person number 2 can be named if person 3 is executed. Correct? So the probability of n given E3 is 1, and then the probability of n given E2 is 0. Those are known. But the probability of n given E1, if person number 1 is executed, the bailiff or the prisoner, or sorry, the prison guard has 2 possibilities. Has person number 1, well, so person number 2 to be named or person number 3 to be named. Good? You understand what I mean? And when there are possibilities, then personality might kick in. I mean, we cannot assume that person number 2, that prisoner number 2 and prisoner number 3 are the same people. And therefore, there might be preference for the bailiff to name one or the other. Okay, so I label that probability as simply P. When there is a choice there, between 2 and 3, there is probability P that person number 2 will be named. Perhaps, for instance, the jailer hates person number 2 and will never name person number 2 when there is a possibility of naming him. You understand? Or perhaps he will always name person number 2 when there is a possibility to name him because he really likes to say that he will be let go. Who knows what? Good? So in general, my formula is P divided by P plus 1. If we assume that the jailer is indifferent and will name person number 2 equally likely as person number 3, then P is equal to 1/2. And then we have 1/2 over 1/2 plus 1, which is 1/3. Then the probability is not modified. Do you agree? If there is no preference, basically I watch. If I know something about the jailer, I watch the signs that the jailer gives me. For instance, if I know the jailer really likes to mention person, really has an affinity for person number 2, and will be very glad to say that person number 2 is going to be let go, then that probability might be 1. Right? If P is equal to 1, observe what happens. If P is equal to 1, then it's 1/2, as Fnu said. It changes your entire calculation. You understand?
Can I ask a question about this?
Of course.
So why was P of n given E3 1?
Because if the jailer has to mention one name, the jailer always has just, jailer is constricted to mention either person number 2 or person number 3. Now, if person number 3 is to be executed, it cannot be named. So that means there is only one possibility, only one choice, right? There is no access to mentioning person 1. If person 3 is executed, then person 2 must be named. If person 2 is executed, person 3 must be named. But if person 1 is executed, there is a choice between person 2 and person 3.
Cool. And then I just have one like more general question. So a little bit in the page before, you had P, like probability of E1 multiplied by probability of n given E1. Is that representing the intersection of those two things?
Yeah, so that's the intersection. You see, always, I do it fast in hopes that you remember how this is calculated. Make sure that you understand multiplication rule. So this means, what does this mean? This means probability E1 and n divided by probability of n. Do you agree? And each of them, I can look at the numerator and I can say, what is this thing? This is the same as, by multiplication rule, as the probability of the unrestricted event E1 times the probability of n given E1 in the numerator, and in the denominator I just break it into 3 possibilities. I just intersect n with E1, E2, and E3, because either E1 or E2 or E3 happen, and or at least n is contained within those parameters. Good. So that's how Bayesian probability works. Make sense? So it's really just an application of the multiplication rule. Why do you multiply probabilities? We learned that as an intersection of events. So make sure you feel that.
Yeah, thank you very much.
Good. Good, guys, you understand? Interesting, right? So, and I hope, at least I can tell you it bothered me. I hope I explained somewhat how I at least perceive this. I perceive this information to mean, you know, once you give more definite information, you are narrowing the universes, clear? And you are just trying to assert trying to guess in which universe you are located among the available universes. And every information narrows the available universes. And probability is just a ratio of desired universes to number of desired universes to the number of overall universes available. Good? All right, so here is a very typical, very famous question. I'm sure you've heard of it many times, Monty Hall problem. So we have a prize behind one of curtains, one of the 3 curtains, either 1 or 2 or 3. Now you pick which is your favorite curtain. Without loss of generality, let's relabel that curtain to be curtain number 1. Agreed? And then the host of the show will open one of the curtains, the empty curtain, and ask you, do you want to switch? Do you stay with your original choice or do you switch? What's the better strategy? P can be equal to 0. Yes, Nishar. P can be equal to 0 in the previous question. Good? So do you stay or switch, guys? Let's see. What do you think? Fnu says switch. So some people want to stay, some people want to switch, person wants to switch, Farhan wants to stay. So usually, guys, when you grab something, you made a decision, you don't like to switch from your decision, right? You're holding something, you don't want to let go. But what's the better strategy? Mathematically, the better strategy is to let go. Now, why is that the better strategy? Why is that the better strategy? Let's see. So let's say that W sub S will be event that contestant wins if the contestant employs the strategy of switching to the offered curtain. And let the other, so the other strategy, we will see what the other strategy is, of course, the complementary strategy of staying with the original choice. Good? So we either have, because we have 2 decisions to make, either a strategy of switching or strategy of staying. Now the strategy of switching works as follows. So let's suppose CK is the event, prize is behind curtain number K. So let's suppose we employ strategy of WS, switch once a curtain is offered. So so what's the probability? So you picked, remember guys, default mode is that you picked curtain number 1. Good? I mean, you can always relabel it, and that's the same thing, of course, if it's another curtain. So what's the probability that you win by switching? So we see that if the prize is located behind curtain number 1, the probability that you win by switching is 0. If the prize is behind curtain number 2, the probability that you win by switching is 1. Do you agree? Because if the prize is behind curtain number 2, the host of the show will open curtain number 3. It's similar to the prison question before. Yes? If the price is behind curtain number 3, the host of the show will have to open curtain number 2. So that means that you will win as long as the price is not behind curtain number 1. You can see even before you apply this strategy. So you lose here, WS given C1. It's the moment when you lose, but in all other moments you win. And the probabilities of C1 and C2 and C3 are all the same. Because you know that they're all the same, then the probability of winning by switching is 2/3. And therefore the probability of winning by staying is just 1/3. Make sense? No? Let me go over that again. I mean, I am having a brain fog, I'm presuming, right? Eternal brain fog, so it's very difficult for me to speak. Now, let's understand, guys, what is the strategy that you win by switching. What do? You always go to the unopened curtain, right? So basically you pick a curtain, one curtain is opened, now you have 2 curtains, one that you're holding and another that you are offered in exchange. You always take the exchange. That's the strategy of switching. Understood? Now, basically then before I calculate, I ask, what's the probability? I mean, I already have that strategy before I play the game. What's the strategy? What's the probability of winning using that strategy? So I write it as probability W sub S, probability of win, given that I will switch once this offer is made. Okay, so then I condition it. You understand? I condition it. I mean, the price is located behind either curtain 1 or 2 or 3. So then that probability, do I need to write it? Let's see. Let me just do it here. So in case it was confusing, then guys, probability that I will win by switching is the same that I win by switching, given that price is behind curtain 1 or curtain 2 or curtain 3. Do you agree? And that's intersection. So what is that? That's the probability of winning by switching and price is behind curtain 1 plus probability winning by switching and price is behind curtain 2 and probability of winning by switching and price is behind curtain 3. You're clear? Now, and I don't like that type of thing. I prefer it in conditional form. So this will be probability of victory by switching given price is behind curtain 1 times the probability price is behind curtain number 1. I employ the multiplication rule. So you understand how I use symbolic reasoning here to say that's the same thing. And plus winning by switching given the price is behind curtain 2, probability of being behind curtain 2. And finally, probability of winning by switching given that the price is behind curtain 3, probability of curtain 3. What do we get? So each of those are 1/3, right? Now let's consider what's the first part. What's the probability I will win if the price is behind curtain 1? Well, I abandon curtain 1 when I switch. You agree? It means that some curtain will be opened. I don't know. It's going to be either curtain 2 or curtain 3. Doesn't matter. I will switch to the remaining curtain and I will lose. You agree? And so this is 0. And this probability is 1/3. So it's 0 times 1/3. On the other hand, suppose the price is behind curtain number 2. Then curtain number 3 will be opened and I will transition to the winning price. So that would be 1 times 1/3. And the remaining situation is the same. I mean, if the price is behind curtain number 3, then if the price is behind curtain number 3, then curtain number 2 will be opened and I switch to curtain 3. So again, I win. So you see, I lose once and I win twice. That's where I get 2/3. That's where I get 2/3. Beautiful. Yes, you can, but then that will be 1/3. If you don't switch, it will be 1/3. And those are mutually exclusive strategies, right? You either switch or you stay. So that means that the probability of winning if you remain at your initial choice will be 1/3. Make sense? Good. So that means that if you select this strategy over the other, you will win more frequently. Of course, I mean, there are all sorts of other things. You might, of course, imagine the show is fixed and they're giving you signs. You know, you might either be paranoid or it's true. And then, of course, the situation is more complicated. Right? Because, I mean, if I tell you it's behind curtain number 2, right? Or it's behind curtain number 1, I'm giving you some extra information. But if the price is placed randomly, with extra information or without extra information, you can at least be assured of winning with probability 2/3. Right? If the price is truly randomly placed behind the curtains. Good. So the next example is rather interesting, guys. I hope you will enjoy it. It's very surprising. At least I was surprised by it. So I picked it from the book called Grapes of Math. So write any 2 distinct numbers on 2 separate sheets of paper. And any 2 distinct real numbers can be any numbers you can imagine. There is no restriction whatsoever. It's not 1, 2, 3. They don't have to be integers. And they can be any numbers whatsoever. There are lots and lots of real numbers. You with me? So the number could be, for example, one of them is pi, another one is √2. And now hide those numbers from me. Don't show it. Good? Now, I will pick one of the pieces of paper and I will look at your number. And then my goal is to guess whether or not the number I picked is the largest of the 2 or the smallest of the 2. Does it make sense? You understand what I will do? I'm not going to guess the numbers. I'm not going to guess which is the second number. I'm just going to decide whether or not the second number is bigger than the number I just looked at. Clear? So I will use my psychic powers. I mean, right? Try to use my psychic powers and see if I can win this game more frequently than you, right? You win if I fail to guess. I win if I guess. Who has the advantage? What do you think? Does anyone have an advantage? Weird, right? But what would your intuition tell you? Well, that's good. Exactly. I don't play games unless I have the advantage. That's precisely great intuition. Usually I don't play games unless I have overwhelming advantage. So here is the situation, guys. Okay, are you ready? This is a strategy that will ensure that my likelihood of winning is bigger than your likelihood of winning, no matter what you do. You have to select 2 numbers, any 2 numbers that are distinct, and I have to decide which of those is biggest, right? I'm going to look at one of the numbers and I will decide if I'm looking at your bigger number or at your smaller number. So this is what I will do. So I will take and generate a random real number. You see, I can do that using any distribution that is capable of generating random real numbers. I can take the normal distribution or any other distribution, doesn't matter. I will generate some number and I will compare it with the number that I observe. Do you understand? So instead of having your second number, I create a random number and I will look, and now I have 2 numbers. If the number I generated is bigger, I think that your other card is containing the bigger number. If this generated number is smaller, I will say that the one I'm looking at is the bigger number. You understand what I'm saying? Do you see, guys, that I have a view of only one of the numbers you wrote? Once you've written those numbers, I have only one number that I'm observing, the other number is missing. I'm generating a random number to replenish the missing number. And I pretend now that I see the full situation. I see the number that you actually have written and the number that was randomly generated. And I compare those two. Do you follow? And I will select the, and I will make my selection based on that, right? So if the randomly generated number is bigger, I will say that the card that I don't see contains the bigger number. And if the randomly generated number is smaller, I will say that that corresponds to the smaller number. Clear? Now let me explain to you why that gives you an advantage. Are you ready? Why it gives me, sorry, it doesn't give you any advantage. It gives me an advantage. I actually wanted to play this game, but then of course it will take too long today. I will have showed you, maybe. So here is the situation, guys. So let's suppose that A is the event that the number that I generate is smaller than both numbers. B is the event that it's in the middle, and C is the event that it's bigger than both. Okay, I will draw it for you just in case you're not clear what's happening here. You see, guys, so there are two numbers that you generate. Here is one number and here is a number, another number. Those are the numbers you have picked. Good. So this region is region A. This region is the region B. And this region is the region C. You understand, guys? In other words, suppose that I generate the number K here below both of your numbers. Okay, then event A has occurred. If the randomly selected number happens to be exactly between the two numbers that you picked, that will be region B. And region C is when the number that was randomly generated is bigger than both numbers. Good. So clearly, because of the way randomness works, I know that probability of A plus probability of B plus probability of C is equal to 1. You see, because I will never pick the numbers that you generated. We will see that later when we talk about continuous distributions. That will never happen, okay? The randomly generated number will not match either one of the numbers that you wrote on the piece of paper, right? So the probability that it will be either below both or between or above both numbers that you picked is 1. With me, I cannot calculate those probabilities. They depend on the distribution and they depend on your selection of the numbers. But I know the sum will be equal to 1. Good. Now, what's the probability that that I win? Okay, with my strategy. You remember the strategy? I will label it as W. So probability of win is probability of win given A, probability A plus probability of win given B, probability B plus probability of winning given C, times probability C. Are you with me, guys? So what is my W? W stands for my strategy. My strategy is to use that generated number and use that as the second available. Understood? I only observe one number and I use the random one observed to make my comparison. So here is the crucial part. What's the probability that I win given that the number I picked is below both of them? You can see intuitively, if it's below both of them, I cannot decide whether or not I'm looking at the smaller number or at the larger number. You agree? I cannot. I mean, because I see I drew those two bubbles, but you showed me only one of the numbers. Am I looking at a larger number or at a smaller number? Really, I have no idea. So that probability is 1/2. I hope you see that, guys. Pay close attention. So that probability is 1/2 times the probability A plus. Now I will write this one first. Similarly, if it happened that the number I picked is above both numbers, If it's bigger than both numbers, again, I do not know if the number I'm looking at is the larger of the two numbers or the smaller of the two numbers. And so when I make this choice, I mean, it's also 1/2. But here the middle one is a little bit strange. Now you understand, guys, what happens in the middle. Now I picked a number. Given that I picked my number in between, what's the probability of winning? Now, if I know that I picked between, so it must be larger than the smaller number and smaller than the larger number. You understand? Yes? So this is a bit hard for me to communicate to you, but I'll try, guys. Imagine that the numbers that you picked are 10 and 20, right? So what happens in probability of winning given that I selected the random number in between? I selected my random number here, okay? So if the number that you have shown me is this, then my using this random number as comparison works in my favor, because I think that an invisible number is bigger, just like the randomly generated number is bigger. So I will win by saying that the invisible number is bigger. If on the other hand, you select, you show me this number, the randomly generated number is smaller. You agree? It's smaller than the number I see, and I'm correct to use comparison between the randomly generated number and the number that I'm seeing. So even though I do not know if you are showing me the bigger or the smaller number, my usage of the randomly generated number for comparison is going to work in my favor. Do you see that? That's the important part, which means that if it happens that the randomly generated number fell between the two numbers that you selected, then I will win. So that's where the probability is 1 times probability of B. And what do I get now, guys? It now is, I can write it as 1/2 probability A plus 1/2 probability B plus 1/2 probability C plus, you see, I split this one into 1/2 plus 1/2 probability B. Do you see that? I just split the 1 times B into 1/2 times B plus 1/2 times B. And in grouping, what is this number? This number is simply 1/2 times 1. So this number is simply 1/2. Do you see that? So my answer is 1/2 plus 1/2 times the probability of event B. And event B is not 0, which means my probability of winning is more than 1/2. I will win more than half of the time. And depending on how close you select the number, if I make you select the numbers far apart, I can ensure that I will win all the time. If I can modify this game slightly, I can force you. I mean, you see, it sounds cooler if I make you select any number, but if I make you select the numbers far apart, I make probability B larger. And I can make this game, I can modify it. If you want to, you can try to modify it in such a way that you can be like a magician. You would always be winning. Like you would think that you're an extra sense, you know. Yeah, I spoke with my friend today about those things. I mean, he's a strange guy. Yeah, so he studied physics and he tried to measure energy emanating from people's eyes using some sort of refractions. And he was telling me about it, and I'm okay. Good. So, do you understand, guys, what this means? Isn't it interesting? Clear? Clear? Now, guys, we talk about something that we forget all too often: independence. Independent events. So generally, when you see that event F occurs, F modifies the likelihood of another event E of occurring. So in other words, the probability of E given F is not going to be the same as the probability of E. In other words, the extra information that we get about the universes will narrow the universes in such a way that the likelihood of E will either be less or will be more. Good? But if it happens that the probability is not changed, we say that E is independent of F. And notice what it means in terms of conditional probability. Probability of E given F, it's just the intersection, the probability of the intersection of E and F divided by probability of F. And if there was no change, it's the same as probability of E. And that means that the numerator, probability of EF, equals to the probability of E times the probability of F. It is multiplication that is much simpler than what we wrote. It's less general. Good? Everybody understands this formula, guys? I hope you do. So now let's try to see that if E is independent of F, then F is also independent of E. You understand? Let's see that. So if E is independent of F, then F is also independent of E. In other words, guys, what do we know? We know that the probability of E given F is the probability of E. No change. And want to show? That probability of F given E is probability of F. So how are we going to do that? Well, probability of F given E, it's the probability of F E divided by probability of E. Good. Which is what? Which is probability of F times probability of E given F divided by probability E. Agreed? But probability of E given F, here it is. It's just probability of E. So it's probability F times probability E divided by probability of E. And that allows us to cross probability of E. And we obtain probability F. Good? So we now see that if E does not affect the likelihood of, if F does not affect the likelihood of E, then the other direction would also be so. In other words, if F does not affect the likelihood of E, E will not affect the likelihood of F. Now, another observation is that if E and F are independent, then so are E and F complement. Okay? If E is not dependent on F, E will also not depend on F complement. And the reason for that can also be easily established. You should remember, guys, that the equivalent form of independence, here they are, right? So E given F is probability E, or probability of E and F is probability of E times the probability of F. Those are the same. You see that? They follow. If I have this, I will have this conditional description. And if I have the conditional description, I will have this. Of course, there is this fuss about division by zero. So probability of events that don't occur, or that occur exceedingly rarely. Just like Grant's visits to this class. Yes, Grant? So probability of E F complement is probability of E minus probability of E intersect F. Do you see that? Oh, good. And this part I can write as probability E, probability F. And so I can factor out probability of E, and we have 1 minus probability of F equal to probability of E times probability of F complement, just like we wanted. So you can see that, that E is independent of F complement because you have this product. Now here is a simple example. So we have two dice, they're fair, and we want E1 to represent sum is equal to 6, and E2 represents sum equal to 7. And F represents that first die will land on 4. So is E1 independent from F? Let's consider probability of E1, probability that we'll get sum equal to 6. There are 5 possibilities. Do you agree? 1 and 5 all the way to 5 and 1. So there are 5 possibilities out of 36 total possibilities. On the other hand, the probability that the sum is 6, given that first die is 4. Now you understand that my sample space is now modified. If first die is 4, only the information of second die is not known. So there are 6 possibilities. And out of those 6 possibilities, only one will work. So it's 1 over 6. Good? But 5 over 36 is smaller than 6 over 36. And therefore, they are not independent. E1 is not independent. If I know that first die is 4, it will affect my probability. In other words, if I know first die landed up 4, the likelihood that sum is 6 is better than without this information. Good? You see that, right, guys? If the first die is 4, my likelihood of winning is 1 out of 6. But if I don't know that, my likelihood of winning is 5 over 36, which is less. So on the other hand, if the summation is equal to 7, guys, will there be independence? Could you calculate before I show you? So now assume that I want the probability of sum equal to 7, and I know that first die was a 4. Does this affect probability? Okay, Jennifer. And therefore your conclusion is that they are independent or not? Great, that's very nice. All right, let's do it together, I hope. You understand, guys, what you do. So first of all, unrestricted probability of E2 is 6 over 36. The answer is then 1 over 6. And the probability that E2 occurs given F is 1 over 6. So you see what happens in the situation. Independence does not mean that that information was irrelevant or did not affect our understanding of what universe we are located in, right? So initially there are 36 universes. So you have the universe 1, 6, 2, 6, all the way to, well, 1, 1, I'm sorry, right? So let me just do it this way. So we have universes 1, 1, 1, 2, 1, 6. Then we have universes 2, 1, 2, 2, 2, 6, and all the way until we have 6, 1, 6, 2, yes, like that. Now, when I have the information, so it just happens that what's the probability of E2? The probability sum is equal to 7. Out of those 36 nodes, exactly 6 of them correspond to the sum being equal to 7. You agree? So it's 1 and 6, 2 and 5, and onwards, all the way to 6 and 1. So there are 6 possibilities, all the way over 36 possible universes. So we get 1 over 6. On the other hand, when I say probability of E2 given that first die is a 4, I restrict the universes to what? So I restrict it to the 4th column. So it's just 4, 1, 4, 2, 4, 6. My number of universes has shrunk. So the information did affect my perception of which universes I might be in, but the probability was not affected. Do you see why, guys? Because well, we shrunk by how much? We shrunk by 6, right? So the number of universes is now divided by 6. We had 36, we now have only 6. And the total possibilities of success were also divided by the same amount. So they occupy the same proportion in my modified sample space. Is that clear? So independence does not mean no information. It just means that this information keeps the desired event in the same proportion to the new sample space. That's what it means. Of course, my point, guys, so independent does not mean the information is useless. No, independent means that this information that if the information is useless, of course, I mean, there is no modification whatsoever, but almost every single thing that you say will actually every single thing that you say will narrow down the possible universes you have. Of course, depends what you mean by possible universes. If it's just if my universes are already reduced to being just dice and the numbers on them, then of course some information will not be visible. But in this case, knowing what came on the first die changes my sample space. It makes the sample space 1/6 of the original. Right? It's just it selects the 4th column in my matrix. So my sample space is 1/6 of the original, but the number of successes was also reduced by a factor of 6. To sum up to 7, I had in the original sample space 6 possibilities. And in the modified sample space, I have only one possibility. Do you see that? So the proportion of the desired event with respect to the modified sample space remained the same as its original proportion with respect to the original sample space. You understand? Good. Now, guys, here is an interesting question. I hope you will find it such. This also reveals the mystery of my icon for this class. I'll show you in a moment. So the question is this, guys. Suppose that E is independent from N and E is independent from T. Clear? E is independent from N. In other words, knowing N does not modify the probability of E, and knowing T does not modify the probability of E. Clear? Here, let me write it. So we are assuming probability of E given N is the probability of E. In other words, N did not modify probability of E. And probability of E given T is probability of E. Again, T does not modify the probability of E. What would you say, guys? Probability of E given that both N and T occur, is it the same as probability of E? So if we know this and we know the second statement, will the third statement follow? Tell me what you think. Okay, yes, with a question mark. In other words, is that a yes? Okay. Okay, 2 people say no. 1 person says yes. I also, yeah, I'm asking for your intuition, guys, of course, right? You can think of it, but what's your intuition? I will explain in a moment. Hopefully it's not because you think my favorite word is no. Okay, Abdel, P of NT, of course it is different. It's usually smaller than each of them separately. But yeah, so you see what people think. Okay, so information N did not affect the possibility or the probability of E, and information T did not affect it. Will you when you combine those informations, will it affect? Okay, Alan says no. So no, you mean no for my question, or you think when the information is combined, it doesn't affect the stance of E? In other words, it's like a trial, right? You bring evidence item 1, and that evidence is not making the case for the prosecution. And then you bring evidence item 2, it's also not making any headway for the prosecution. Will the combined evidence 1 and 2 make a headway? That's the question. Okay. Not necessarily independent. All right, guys. So you're a boring bunch, I see. Not many of you are writing anything. Okay. Let me show you my true nature. I hope you can see it. Can you see it? Let me stop the camera. Here it is. Yes. Let's recall the story of Little Red Riding Hood. Right? That will teach you some probability. So suppose that Little Red Riding Hood, she meets several animals on her way to grandma from the forest. 9 animals. 6 of the animals have big eyes. 3 of them have long noses, and 3 of them have sharp teeth. Having taken my probability class, she draws the following diagram, right? So here are the animals having, what is E? Big eyes. So E is big eyes. And then 3 of them have sharp teeth, and 3 of them have long noses, okay? So what is the probability that this person that ate her grandmother has, what's the probability he has big eyes, given that he has a long nose? Right, so probability of E given N is 2/3. You can see here is a long nose. You can see E given N. So if N occurred, E occupies 2 nodes, right? So probability of E given N is 2/3. And probability of E is altogether 6/9, it's 2/3. So the ratio of E with respect to the sample space is 2/3. Do you agree? Which means that the probability that he has big eyes, given that he has a nose, a long nose, is not affecting him having big eyes, right? Scary big eyes. So it's the same probability. Now let's consider the probability that he has big eyes, given that he has sharp teeth. So let's see here again, 2 out of 3. If he has sharp teeth, the probability he will also have big eyes is 2/3. Yes? Now, on the other hand, what's the probability that he has big eyes, given that he has a long nose and sharp teeth? Well, let's see. Long nose and sharp teeth, right? Here it is. The intersection is just 1 point. It's 1. You understand, guys? So now we know for certain that we have a wolf. Good? Clear? That's mathematical summary of Little Red Riding Hood. So you are too logical, so of course it didn't surprise you, right? It's just completely obvious. Correct? Wonderful. That, I suppose, is a good trait. All right, guys. So what do we begin to do next? We begin to talk about an important topic, about expected value, or average, or stereotyping. So first, for that, we need to understand what is a random variable. So we are in lecture 4. Look how quickly time moves. Once we are done with chapter 4, you have your second exam. Yes. So here is the situation. Yes.
Exam 2 is also take home, right?
Yes.
And what about exam 3?
And exam 3, we shall see.
Yep.
right? We shall see, right? So there is, in addition to take home, there is mostly take home. But if I see that people are, you know, cheating, then it will be interrogation, right? In other words, I'll give a question. It will be a Russian style exam, and it was like I'll be deciding if you understand the material. That's not fun.
Sure.
Yes. Good. So here is, guys, the situation, right? So let's play Russian roulette. So in a Russian pistol, in a pistol, there are 7 chambers typically, and what do? You take a revolver, you place a bullet, you roll the drum. Good. Every time you press on the trigger, before you press on the trigger, you have to roll the drum. Otherwise, I mean, so that the probability of getting the bullet is always 1 out of 7. Good. So of course, guys, you know, the precise situation of where of which round is fired is not of immediate interest. Do you agree? So there are chambers 1 through 7, but I don't so much care about the chamber that was fired as opposed to whether it had a bullet or not. Good. So I reduce my sample space by this function x. Okay, so here is my original sample space. It consists of outcomes 1 through 7, but the only outcomes I care about for this game is bullet or no bullet. Great. So let's say that in chamber 1 there is a bullet, and in the remaining chambers there is no bullet. So my function will compress 1 into B and compress the remaining chambers into N, no bullet. Right? Now, you can see that, in other words, playing the Russian roulette is similar to playing another game that has only 2 outcomes, where one outcome has probability of 1 over 7, that's the bullet, and the other outcome has probability of 6 over 7. You see, it's as if I melted together all those chambers into the 1 letter N. You see that? And I added up the probabilities. Good. So X is going to be called a random variable. In other words, it's really just, when you think of random variable, it's somewhat of a bad name. It's just a function that transforms one sample space into another more interesting sample space, one that you more immediately care about or is more useful to you for some purposes. You will see many examples of that. Does it make sense, guys? So I don't care so much that the outcome was 2, 3, 4, 5, etc. Mostly it's interesting that it had no bullets. So it's really, now I melted, or I fused that sample space into another S star that has only 2 outcomes. And I modify those probabilities for the outcomes are not the same. Whereas here, each outcome is equally likely. Good. So the nice way to think about what happens in S, you can think that S consists of pebbles, and pebbles is the weight, probability weight on it. So we have 7 pebbles, each of them weighs 1 out of 7. Good. They are weighing the same amount. And what we do when we apply X, we might fuse some of those pebbles together and therefore fuse their weight. In this case, we fused 6 pebbles together and we get 1 super pebble in S star that consists of, that has a weight of 6 over 7. Good. That's really what happens. So now we can define, so it's like X is crushing those stones together. So X has to be just any function from S onto any S star that is onto. And then it induces this function X, if it's onto, will induce a probability on the set S star. So S star could be any set to which, of course, from a sample space X is onto. In other words, it's able to produce any element in that S star. And S star will now be made into a sample space by the following feature: the probability of an outcome Y, if Y belongs to S star, then probability of Y is the probability of the inverse image of Y. In other words, what does it mean, guys? So what's the probability of N? It's the sum of the probabilities. It's probability of inverse of N, which is 2, 3, 4, 5, 6, or 7, right? So that means I add up all those probabilities that are mapped here. Make sense? So it's just the summation of all the probabilities where X maps this little x into Y. Clear? You understand, guys, what's happening so far? Nothing difficult, correct? And if I'm wrong, then let me know now. It's very important. All it is just a function. You understand? What we do is we collapse those pebbles together, and then what's the induced probability on n? It's just I just look back at what was melted into n, and add the probability, add the weights of those pebbles that were melted together to form n. Good. That's really all this is saying. So that's how this space was induced. You see that 6/7, I could have figured it out because it means either this, that, or that. Good, so here is a first example. 3 balls randomly selected with replacement from urn containing 20 balls, and they are numbered 1 through 20. If we bet that at least one of the chosen balls has a number as large or larger than 17, what's the probability that we win that bet? So notice in that bet, guys, we sample three balls. You agree? And we are only interested in the largest ball, in the largest denomination. So I will say X, my random variable, is possibly the largest value that was picked. So X is either 3 or 4 or all the way to 20, right? Because I sample 3 of them, X can never be less than 3. So then I can calculate my probability. My probability that I win is probability that X is bigger than 17. Now that means it's the probability where X is 17 plus the probability where X is 18 plus the probability where X is 19 plus the probability that X is 20. Good. In other words, either the largest picked is 17 or 18 or 19 or 20. And then I win. Now, what's that probability? So first of all, how many ways can I select a sample of 3, given that 17 is my largest? If 17 is my largest, I already picked 1 ball, and I can pick 2 more from the 16 that are below, right? So it's 16 choose 2. Everybody says that? The 16 choose 2 means because in my sample space, it contains information about 3 balls picked. I arrange them in order from smallest to largest. And if I know the largest, I just need to select additional 2. Good, so that's why it's 16 choose 2. Now, if the largest is 18, then I can select from 1 all the way to 17, and I need to select 2. And doing that all the way to X equal to 20, I have 19 choose 2. I have the numerator. Now the denominator is simply 20 choose 3, right? Because I can pick any grouping of 3 balls. My universes are just any grouping of 3 numbers placed in order, right? You still remember, guys, the Kafka protocol, correct? Because you already, have you finished the exam already or almost finished? I think we have what, 1 more week or something, yes? Good. Okay, oh, great. And this is the probability, it's slightly over 50%. So today's lecture, I think, is over, right? I will not hold you longer, unless, of course, you're interested in the next episode of What, When, Where, or you are really in the mood of listening to that song I sent my friend in response to his discussion about extrasensory things, which I tend to be annoyed by. It's in Russian, so I'm not sure if you would be annoyed by that song. It's very beautiful and deep, but in Russian. How to submit the exam? Well, guys, there is, first of all, you all know how to make it a PDF file and to title it correctly and to include the exam format onto it. So I don't want to see if you can take photographs and post it into Word and then convert to PDF. It's up to you how you do it. But I want one file and I want it to be titled in a particular way. That will be easier for me to grade. Good. I will then look at the PDF. I'll make comments there. Good. And how to submit it? For sure, you can do it by email, but I might consider you uploading it to what do you call it, to Blackboard. But the thing is, I don't like using it. So it might be by email, it might be by Blackboard, it might be both to ensure that you have it. But make sure that it's ready, titled correctly, P, P first name, sorry, last name, first name, and what exam, just like I said in the comments. So follow the instructions carefully. Good? If you want to, you can show me how you submit. If you want to, at some point, show me how the exam looks like. Good. All right.